All right, Joachim, are you ready?
I'm ready, yes.
All right, so very good. Good day, everybody. We have got about almost about 100 people here. So can I ask you, before I introduce Joachim, to mute yourself during the talk? And because, yeah, as I said, we have a lot of people here. In case you have questions, just send them on the chat that eventually we are going to get to the questions. So yeah, it's a great pleasure to have Joachim Cuntz as our first speaker here today. And he is going to tell us about the algebraic approach to KK theory. Joachim, please.
Thanks very much, Rusbe, for the introduction, and hello to everybody. So the topic of my talk is a long-term project in which I was involved for many years, over more than 30 years, I think. And it starts with Kasparov's theory. Since here, this is a seminar on non-commutative geometry, I assume that most of you have some basic idea of what Kasparov theory is. So Kasparov introduced his bivariant K theory in the 1970s. And the Kk theory associates with a pair of C-star algebras, let's say a separable C-star algebras, an abelian group, denoted by KKAB. And the fundamental property of this association is that you have the product. So you have a product if you have an element of Kk of A1, A2, and another one Kk, A2, A3. You can take a product and get an element in Kk of A1, A3. And this is associative. So the best way to view a Kk is as a category where the objects are C-star algebras, and Kk of AB is the set of morphisms. So it's an additive category. And the important fact is that this theory generalizes K theory, topological K theory for C-star algebras, and K homology at the same time. When you plug in the complex numbers in one of the variables, you get K theory and K homology. And then it has very, many nice properties, such as homotopy invariance, stability. Stability means when you tensor by the compact operators, it does not change. It has long exact sequences in both variables, and it's spot periodic. Well, here is no index, but you can also define KKN, and then it's 2 periodic in the index. And these properties have the effect that you can actually compute these groups in many cases. Now, Kasparov was motivated by applications in index theory and yeah, mainly from index theory. And so his methods kind of start from the idea, which is also due to Atiyah, to start with abstract elliptic operators as basic objects, and then to define elements of Kk using such what he calls Kasparov modules. So for a pair of C-star algebras, then Kasparov considers modules, Kasparov modules, nowadays called Kasparov modules. And in fact, you have a odd Kk, which is Kk1, and even Kk, Kk0. And for the odd Kk, Kk1, the representatives are odd Kasparov modules. And now in the following, I want to analyze the algebraic content of these modules. So it is a fact that, I mean, a priori, an odd module consists is a pair. It's a homomorphism from A into the bounded operators on the Hilbert module, standard Hilbert module L2 of B over B. So you have, oh, sorry. Let's see. No, it does not work. So let me do it this way. No, okay. Oh, no. Oh, but I'm sorry. So maybe I should start it again. Anyway, so you have a pair, you have a homomorphism from A into the bounded operators on the standard Hilbert module L2 of B, which consists of L2 summable sequences of elements of B. And in B of L2 of B, you have a self-adjoint operator. Actually, in this case, you can take a self-adjoint projection. And the key condition is that the commutators of this operator with the image of, let me try to see if I can get it. Okay, so at least, so this here, okay, well, no.
Maybe you can go back.
Yeah, can go
Sometimes
back.
there's a back key.
Okay, I'm sorry. So I cannot really point out where I am. So, okay, so the key condition is that the commutators of this operator with the image of A under the homomorphism should be compact. There's a notion of compact operators on this Hilbert module, and so the commutators should be compact. Actually, the algebra of compact operators on this standard Hilbert module is as a C-star algebra isomorphic to the tensor product of the standard compact operators on a separable Hilbert space by B. Now, from an odd module, you can construct an extension. And that's also something used by Kasparov. Namely, you can multiply the operator P with the image of A under phi on both sides and take the C-star algebra generated by this. And if you are a little bit careful, then well, it will contain the compact operators. And the quotient will be A. I mean, if you just modify the P possibly by a trivial operator. And so you get this extension, and it's not just any extension, it comes with a completely positive splitting, which goes to X goes to P times phi X P. So it's an extension with a completely positive splitting, which you get from an odd module. Now let's have a look at an even module. An even module is again a pair of a homomorphism and a self-adjoint operator, but this time we take a set mod 2 graded Hilbert space, namely the direct sum of L2b by itself, and the bounded operators on this. And the homomorphism should be of degree 0, so it's a diagonal homomorphism. It consists of two homomorphisms, alpha and alpha bar, and then you have a self-adjoint operator F. And I mean, the fact is that you can always modify, you can always assume up to homotopy and addition of degenerate elements, modules, that the F is of the form, as a standard form, namely is just the off-diagonal operator 0, 1, 1, 0. And again, you want that the commutators of this operator with the image of phi should be compact. Now, this time compacts in this direct sum of the two Hilbert modules. And well, what does that mean? If you look at the commutator of the image under alpha alpha bar and this F, you get just the off-diagonal thing, which alpha x minus alpha bar x. And so the condition that this commutator should be compact means exactly that the difference of alpha x and alpha bar x is compact for each x. Okay, so that's what you get from an even module. And this is, I call this a quasi homomorphism. So it's a pair of two homomorphisms. So here you have two arrows from A into this bigger C-star algebra, which contains the compact operators as an ideal. And the condition is that the difference of the two homomorphisms should map A into the ideal. So that's what I call a quasi homomorphism. Okay, now let me continue with the even case first before I come again to the odd case. So in the even case, we have seen that the even Kasparov module gives rise to a quasi homomorphism into the compact operators. And the fact is that there is a universal quasi homomorphism. Namely, let me try again if I can mark, but probably it will not work. So let me have a look. Okay, this time it works. Okay, so we look at the free product of A by itself, and we denote the free product by QA. And the free product comes equipped with the two natural inclusion maps iota, iota bar from A into the free product. Now, little q of A will be an ideal in capital Q of A in the free product, and it's defined as the kernel of the natural map from the free product to A. I mean, Q of A, the free product, has a universal property that for any pair of homomorphisms, there's a map from A, there's a map from QA into the same target. And so here, so you take twice the identity, you get a homomorphism from QA to A, and little QA is defined as the kernel of that map. It's also the ideal generated by these differences. Namely, the differences, of course, the differences will be in the kernel in little QA, and in fact, it's easy to see that QA is the ideal generated by these differences. And so you get a quasi homomorphism. Namely, you get these two arrows here from A into this bigger algebra, and here's the ideal. And the difference of these two arrows maps into the ideal. So that's a quasi homomorphism. And I claim that this is a universal quasi homomorphism. It has a universality property. So namely, take any quasi homomorphism, alpha alpha bar, from A into some ideal I, and then you get a commutative diagram. Namely, here you have the QA as an ideal in capital QA. You have the two arrows, iota, iota bar. And here you take, as I said, QA has a universal property for pairs of homomorphisms. So the pair of homomorphisms alpha, alpha bar gives you a map from QA to the bigger algebra in the given quasi homomorphism alpha, alpha bar. And of course, it will map if you compose this with if you compose this map here iota iota bar with alpha alpha bar, you get here alpha alpha bar, and of the difference it goes to the ideal. So this here is a map from the quasi homomorphism, and then if you restrict the map from QA to E to the ideal, then of course it will map into the ideal in the given quasi homomorphism, and the map here that you get from the universality is called the classifying map of the homomorphism. And I claim that this classifying map contains all the relevant information on the quasi homomorphism and even on the original even Kasparov module. I mean, this has to be shown, but it's not that difficult to show that. So by relevant information, I mean, you consider the Kasparov module up to homotopy and addition of degenerate Kasparov modules. So basically, everything is contained in this classifying map. So if you go back, if you have a Kasparov module as before, alpha consisting of alpha alpha bar and the operator F, then we get a homomorphism. The classifying map is a homomorphism from QA to K tensor B. And I claim that, well, what I said is that this homomorphism contains all the information on the Kasparov module. So in particular, two even Kasparov modules are equivalent if and only if their classifying maps are homotopic. So now Kasparov defined Kk of AB as the homotopy classes or equivalence classes of all even Kasparov modules AB Kasparov modules. And what we have seen is that this is equivalent to considering all homotopy classes of homomorphism from the algebra QA to K tensor B. So these square brackets is standard notation to denote homotopy classes of homomorphisms from this algebra to this algebra. So that's a description of KK of AB. KK stands for, is shorthand for KK0. So when I write KK, it's just KK0. Okay, so that's what kind of algebraic description of KK, just based on this algebra, on this universal quasi homomorphism. And now we can have a look at the composition product. So assume that you have a homomorphism representing an element in KK-A1, A2, and another one representing an element in KK-A2, A3. And we want to compose these two. So we want to find an arrow from here to here and then take the composition of these things. Now in the middle, it doesn't look so bad because you have A2 in each case. And but then you have some additional declaration, namely here you have the compact operators, tensor product with K, and you have the declaration by little q. So you cannot immediately compose these two things. But what you can do is, well, here tensor product with K is missing, so we just add this tensor product with the compact operators to make it more composable. And here little q is missing. Here we have a q. So of course, if you take the tensor product with compact operators here, you also have to take it here in order to get a map, in order to get this map from the second to last algebra to the last algebra. And in the same way, here we want to get a map from here to here, and we want to introduce an additional little q to make a composition possible. So little q again is a functor, so we can take the homomorphism that we had and just put a q, and then we get a map from q of A1 to q of K tensor A2. And now this is quite nice because by universality, actually, it's very easy to see that there's a natural map from q of K tensor A2 to K tensor Q A2. I mean, this is kind of trivial from the universal property. So, and this can now be, so you now have a composition, a map from q of A1 to K tensor A3. So this is, so q of A1 I denote by q squared of A1, and this goes to K tensor A3. Now K tensor A3 is already quite nice because it's of course well known that K tensor K is isomorphic to K. So we get a map from q squared of A1 to K tensor A3. And now we want to reduce also the q squared of A1 to just q if possible. And this is in fact possible, namely there is, one can construct, this is a so-called technical theorem. Kasparov had a technical theorem on which he based his product. And this here is another version of the technical theorem, a little easier to prove than Kasparov's technical theorem. Namely, you can show using C-star algebra methods that there is a natural homomorphism, well, there is a homomorphism from Q of A, not quite to Q squared of A, but to the 2 by 2 matrices over Q squared of A. And this is kind of a homotopy inverse to the natural map from Q squared of A to Q of A. I mean, this map from Q squared of A comes from the fact that Q squared of A is a subalgebra of capital Q of A. And from capital Q, you get a map just deleting one of the two copies. And this is a restriction of this map from capital Q. So this is a very natural map. And so what you get, in fact, is that up to a stabilization by 2 by 2 matrices, little q of A is homotopy equivalent to little q squared of A. So, so that means that the homomorphisms that we got from q squared of A1 to K tensor A3 can be reduced up to homotopy to homomorphism from Q of A1 to K tensor A3, because we can replace K tensor A3 by K tensor A3 by homotopy or isomorphism, and Q square of A1 we can replace by Q of A1, but this is exactly Kk of A1 A3. So, and this gives you a product from Kk A1 A2 times Kk A2 A3 to Kk of A1 A3. And it's basically, from the definition, it's immediately clear that it's associative. Okay, so that's the construction of the product. And well, this approach is, I mean, Kasparov's approach, of course, is very useful because it can be readily applied to many problems in index theory or things like the Baum-Conn conjecture and also the equivariant case. But this approach to Kk also has its virtues, namely it simplifies quite a few of the arguments for many key results, like the basic results about Kk theory can be proved quite easily in this approach. So bot periodicity, long exact sequences, Thom isomorphism, Pinch-Navarro-Kolesko sequence, computation of Kk for the reduced D-star algebra free group, and recently it has also been used for in the classification of nuclear separable C-star algebras. So in many of these cases, you get quite simple arguments. And there is also another application is for index maps. By index maps, I mean connecting maps in the long exact sequences that you get in Kk. Okay, I have to put that back for a moment, because for the index maps, you have to understand Kk1. So you have to understand the odd case. From the odd case, you get, in many cases, very easy descriptions of the index map, of the connecting map in the long exact sequences. Okay, so let's now we come to the odd case. An odd Kasparov module, as I told you before, gives you an extension with a completely positive splitting. So it's an extension of the form where the ideal is K tensor B, where B is the second algebra, and the quotient is A, and you have a completely positive splitting map, linear map S, which splits this extension linearly. So it's a CP means completely positive. You have a completely positive linear splitting S. And the definition of E was on the previous slide. Now, again, just for quasi homomorphism, we have a universal extension. Namely, you can consider the tensor algebra, non-unital tensor algebra over A. And we want, so that's now, first of all, purely algebraic, but you can complete it in a very natural way to a C-star algebra. But we still want to keep the condition that the natural linear inclusion of A into the tensor algebra should be completely positive. So there is a natural C-star norm, namely you take the subprimum over all C-star semi-norms on the tensor algebra, which has a property that the map, the linear map from A into the tensor algebra still remains completely positive. And then you take the subprimum over all such C-star semi-norms, and you get the tensor algebra, which is a C-star algebra. And from the tensor algebra, you get a natural homomorphism to A, which is just in the tensor factors, you multiply all the elements together. So it's just a multiplication map. So that's a natural homomorphism from the tensor algebra to A, which is also passes to the C-star algebra completion. And the kernel of this map is the universal ideal in an extension, and it's denoted by JA. Now, here's a remark. I mean, this is important, but not so important for my talk today. Namely, there is a connection between the universal quasi-homomorphism and the universal extension, which also explains in a way why Kasparov has this Z2 grading everywhere. Namely, the tensor algebra and the ideal JA, they are exactly the even parts of the algebra QA, which I mentioned before, the free product, and the ideal QA. So there's a close connection between these two things. And this is compatible with the C-star algebra completions. Okay, so now let's see why this extension, why this gives us a universal extension. So consider any extension E of A, which has a completely positive splitting. So you have a completely positive splitting. And I claim then there's a commutative diagram, just as before for the universal quasi homomorphism. So we compare the given extension with the universal extension, which I claim is a universal extension. So here we have this, we have the map from A to A, the identity map, but down here we have the map S, the completely positive splitting from A to E. Now, what's the map from the tensor algebra to E? Well, it maps the generators of the tensor algebra. The tensor algebra is generated by the first copy here of A by S. So, and this gives you a homomorphism. So it's only linear on A, but on the tensor algebra it's a homomorphism. And then this part of the diagram will be commutative, but then this implies that immediately that the kernel of this map has to be mapped to the kernel of this map, which is I, and we get again a classifying map. And so we get a classifying map for any extension. And again, I claim that this classifying map contains all the relevant information on the extension and also on the original Kasparov model. I mean, it's not so difficult to show that if you modify, I mean, from the extension, you get the Kasparov module back up to homotopy and addition of degenerate elements and so on. Okay, so now Kasparov defines Kk1 of AB as the equivalence classes of extensions, or of course the equivalence classes of odd Kasparov models. But as we have seen, both things are classified by homomorphisms from this universal ideal to the ideal. The ideal in this case should be K tensor B. Okay, so these are exactly the classifying maps for the odd Kasparov models. So the odd Kasparov module is completely determined by its classifying map, which is mapped from the universal ideal JA to the algebra K tensor B. And then, of course, Kk1 of AB is simply equivalent to the set of all homotopy classes of such classifying maps. And there's also, now we come to what I said before, namely the index map. We get here, if you have an extension, you get the classifying map and the corresponding element in Kk1. And it's a fact which can be used in order to compute connecting maps in many cases. So you have an extension, you have an extension, you get the corresponding long exact sequences in Kk in both variables. And the point is, which is not very difficult to see, that the boundary map in these long exact sequences is exactly the product by the Kk1 element associated in this way by the extension. Okay, so I won't say much more on this, but just to explain the point about index maps and connecting boundary maps in long exact sequences. Okay, so here's just a repetition of what I just said, namely the classifying map contains all the relevant information on the original Kasparov module. And so we get Kk1 of AB is just the set of homotopy classes of maps from this algebra JA to K tensor B. Now let's again look at the product. So we have a homomorphism from J of A1 to K tensor A2, and a homomorphism from J of A2 to K tensor A3. And we want to compose these two maps in order to get a Kk element. Now, what can we do? I mean, it's a little bit similar to the previous situation. So in the middle, we have A2 in each case, so which is it's not so bad. But here we have an additional K, which I have to we should have to make up for by putting a K here. And but if you put a K here, also a K here, so we tensor this homomorphism by K. And again, it's nice that K tensor K is really not very troublesome because it's isomorphic to K. But here in the middle, we have a J. So to make up for that, we have to put a J here. And again, it's very easy to see that there is a natural map from J of K tensor A2 by universality to K tensor J of A2. I mean, that comes immediately out from universality. So what we get from the composition is a map from J2. So again, I denote by J of A1, J2 of A1, J squared of A1 to K tensor A3. And it's a fact that this map corresponds exactly as a classifying map for the two-step extension obtained by Uneda product of the two extensions corresponding to these maps. And this Uneda product is just a concatenation of extensions. So it's a very natural thing to consider. And okay, so that's what we get. It's kind of a product, but okay, but of course it's not. This time we cannot reduce J2 to a J. In the previous thing, in the even case, we had reduced up to homotopy Q squared of A to Q of A, but this is obviously not possible. I mean, it cannot be true because J squared is quite different from J. But we don't need it. So there is a different way around this, and which simplifies, in fact, a lot of things. Namely, there's another version, another nice extension, which is very fundamental in KK-theory, K-theory, and so on, namely suspension extension. You take the functions, A-valued functions on the unit interval that vanish at 0. In there, you have the suspension of A, which are the functions, which consists of the functions vanishing at both endpoints. So that's the suspension. And so by what I said before, there is a classifying map. We have a classifying map from the universal ideal J of A to the ideal in this extension of A. So that such a classifying map always exists. And we can use this map to get a natural map here from, so J is also some kind of suspension. So here we take the n-fold J extension, here we take the n-fold ordinary extension, and I claim that there is a map. Now on the right-hand side, we go one step further with both suspensions, and I claim that there's a natural map, namely, well, what do you do? Well, first of all, J is a functor, so you put J on both sides. Then on the right-hand side, you get J of Sm, but there's a natural map from J of anything to S of anything. So there's a map from J of Sm of K tensor B to Sm plus 1 of K tensor B. And so this way you get this natural map from Jn of A1 Sm of K tensor B to one step further in the sequence, namely n plus 1 to n plus 1. And then we can take a limit. So we can define Kk of AB. We take the limit over J. So here we go each time one step further with a J. And we take the inductive limit of these abelian groups. And this is now a definition, first of all. But it's not a definition because it's really not so difficult to show that this is really the KKN that we had considered before. Namely, it reproduces the KK0 and the KK1, which I had described before, and it also coincides, of course, with Kasparov's definition. And all this is not really very difficult to show. And so the Uneda product, you see the Uneda product here. By the Uneda product, we got this map from J squared of A1 to K tensor A3, and this gives you a map from. So this product gives you a map from elements in KKN of A1, A2, KKM A2, A3 to KKN plus M A1, A3. I mean, just doing this composition up here, and I mean, okay. And replacing K tensor K by K. Okay, so that's a very natural and very easy product. It's completely algebraic. It doesn't need any technical theorem from C-star algebras. It's just algebra and homotopy. Okay, algebra and homotopy. So it's really an algebraic definition of the product. So that's the algebraic definition. And so the product, again, we get a category, a Z-credit category, and the unit product gives you the product of morphisms in the category. And you can take this definition as a basis for Kk and derive the properties of Kk from, you can derive the properties of Kk from this definition. And in fact, it's not really so difficult. Well, first of all, it's functorial, of course, that's clear. It's homotopy invariance is, of course, trivial because we take homotopy classes. Stability tensoring by the compact operators does not change anything. I mean, it's also pretty clear because here we have K, we have already stabilized. What is a little bit more difficult is half exactness, but that also comes, you know, once you define something by homotopy classes, you get mapping cone, exact sequences, and then you can use the product to reduce the mapping cone of the inclusion of the ideal to the ideal and so on. And so by standard methods, you get the key properties of Kk. You also get Bott periodicity, but that's not such a fundamental, I mean, that's just a consequence. So the Kk will be two periodic in N. So in fact, you have only two groups, namely Kk0 and Kk1. And also, it's then completely clear that Kk is universal with the properties, with the three blue properties, homotopy, invariance, stability, and half exactness, because if you have any functor from the category of, let's say, separable C-star algebra to additive category with these three properties, and if you look at the definition, so the definition is here. If you look at the definition, then such a functor will always forget homotopy classes. So homotopy classes for such a functor is just the same as morphisms. By stability, you can forget the K, but then by half exactness, you can argue that again, the suspension just changes the degree by 1, and the non-commutative suspension also just changes the degree by 1. And so it will just be the same as, so it's clear that under such a functor with these properties, these will be just the morphisms. Okay, so that's really obvious. And now let's see. So what did we use in order to construct the Kasparov groups? Well, we used a category of topological algebras. We used a notion of homotopy classes of maps. We used a notion of suspension, a notion of stabilization, and a version of the compact operators, and a universal, a class of extensions that admits a universal extension. In this case here, it was extensions with a completely positive linear splitting. And so this class admits the universal extension which I described. But the point is, once we have all these data and the algebra, two algebras A, B in the given category, then we can always make this definition, and which now to distinguish it from the capital Kk from before, I denote it by little kk, and we can define Kkn of AB. It's exactly the same formula that we had before. We just take the limit over the maps from the non-commutative suspensions of A into the stabilization of the commutative suspensions of B and the homotopy classes. And so that's the definition which we reproduce literally from above. And then one can show, then it comes, I mean, just from the description of the Unida product, I mean, we can do exactly the same what I said before, and we always get a product. And so we get a category, a set credit category, and this functor Kk, which I define this way, will be homotopy invariant. Again, because I use homotopy classes of maps, it will be stable because I stabilize by the compact operators, and will be half exact because it works for mapping class, mapping cone sequences and so on. And moreover, the Kk, if you look at Kk0, which which is similar to the capital Kk0 that we had before, again, this will be the universal property with these properties on this category of Algebras with these given structure elements, namely suspension, stabilization, and extensions. And one can also, if in the complex case, if for the standard choices of homotopies and so on, it's usually a pod periodic. Okay, so that's just a repetition, namely definition of little kk and of AB. And okay, now let's look at some examples. Okay, I mean, we can take different categories of algebras and different structure elements like suspension, compact operators, and classes of extensions. So first example, the category of C-star algebras. We take suspension and stabilization as above, but now this time we allow arbitrary extensions, not just extensions with a completely positive splitting. And one can show that there exists again a universal such extension. Well, you have to complete the tensor algebra in a different way. And in this setting, the definition of Kk gives, of course, no surprise, gives the E-theory introduced by Alencon and Nigel Hickson. And so that's the universal functor that is also half exact for arbitrary extensions of C-star algebras. In fact, one can even, I mean, that's a big advantage of Kasparov theory is that it's also equivariant. One can even do it for equivariant in the equivariant setting for arbitrary locally compact groups, but that will be not so elegant and maybe not so useful, but one can do it. I mean, so you get you can also reproduce Kasparov's equivalent theory by using the suitable stabilization and suspension and so on and extensions. Okay. Now, as a second example, consider the algebra of the category of Banach algebras, let's say over the complex numbers with ordinary notion of homotopy and suspension. But stabilization, this time it will be, we could take a tensor product by the C-star algebra of compact operators, but here it would be more natural to take the product, projective tensor product, let's say by Hilbert-Schmidt operators. There are many possible choices, but Hilbert-Schmidt operators is kind of particularly a nice choice. So, the key point about stabilization is always that it should contain all finite matrices over the algebra. That's the key point. And then it should be completed in some way in the corresponding category. And we consider all the class of all extensions of Banach algebras that admit a continuous linear splitting. Then we can define the functor Kk just as above, as this inductive limit. And it will have the properties from the previous slide. It has long exact sequences, it has a product, and it's also pod periodic, and it satisfies Kkn of C, A is the ordinary K-theory of the Banach algebra. I mean, Banach algebra has a well understood notion of topological K-theory. And so it reproduces in the second variable the K-theory of the Banach algebra. But okay, but the key setting, I mean, what I tried to do mainly in the beginning was to develop a functor such as Kasparov's functor for locally convex algebras and using only C infinity homotopies, not continuous homotopies, but C infinity homotopies, smooth homotopies. And the motivation was to make a bivariant K-theory available for such algebras, because such algebras, of course, occur in many applications. You have algebras of C-infinity functions on smooth manifolds, or you have algebras of pseudo-differential operators and so on. And one would like to have a theory which also applies to such algebras. And but also a key motivation is that for such algebras, one can hope to construct a bivariant adjoint concharacter from the bivariant theory into the bivariant version of periodic cyclic homology. And such a bivariant adjoint concharacter cannot exist for C-star algebras, because it's well known that periodic cyclic homology for C-star algebras gives you a nonsensical results, so that it wouldn't make sense for C-star algebras. But for locally convex algebras with C-infinity homotopes, I mean, HP star is invariant under C-infinity homotopes, but not under continuous homotopes. So that's the point why you cannot hope for a bivariant joint character on the category, from the category of C-star algebras to periodic cyclic homology, but it will work for locally convex algebras with C-infinity homotopes. Okay, so that was the motivation. And in fact, the construction will be exactly what I just described, namely, again, another application of this general formula. And so let's just go through the ingredients of the theory of the category again in a little bit more detail. So we look at the category of locally convex algebras over the complex numbers. And so we look at general locally convex algebras where the semi-norms are not necessarily submultiplicatives, but the condition is that the multiplication should be continuous. So that means that for every semi-norm defining the topology alpha, there should be another semi-norm beta such that alpha of xy is dominated by beta of x, beta y. So that means that the multiplication is continuous. And homotopy is C-infinity homotopy. So also the square brackets will now denote homotopy classes for C-infinity homotopy. And the suspension, again, will also be defined using C-infinity functions. So it's defined as before, but simply replacing continuous functions on the unit interval by C-infinity functions. And at the endpoints, we also want all derivatives to vanish, not just a function. And the stabilization, again, it wouldn't make sense to stabilize by the compact operators, C-star compact operators, because in cyclic homology that would kill everything. So, but we can take, for instance, the projective tensor product by the Hilbert-Schmidt operators again. And the extensions are extensions of locally convex algebras. And here again, we assume that we have a continuous linear splitting. And okay, then there is a tensor algebra. We can again complete the tensor algebra as a locally convex algebra in a suitable way. Again, using basically just all possible semi-norms that satisfy a certain condition. And so there's a natural choice for the locally convex completion of the tensor algebra. And with all these ingredients, we can now make the definition exactly as before. So it's exactly just the previous definition reproduced with these structure elements, and we get a bivariant K-theory. And so that's here. And again, this functor is universal on the category of locally convex algebras with the properties of being homotopy, invariant, stable, and half exact. It has all the usual properties of KK theory, and the proofs are basically always the same also. The key, very important point is that KK0 of C comma B is kind of computable. Namely, it's just K0 of a stabilized algebra. In particular, if B is a nice algebra, like a Fréchet algebra or a Banach algebra, then we just get the ordinary K0. And in particular, KK0 of C comma C is just the integers. I mean, that was for a long time was in fact a problem to develop the theory in such a way that the coefficients KK0 of CC is not too big. And this was achieved here by tensoring on the right-hand side by the Hilbert-Schmidt operators. And that was done in a joint paper with Andreas Thom. Okay, also on a bootstrap of class of C-star algebras with smoothed up algebras, actually the KK invariance of the smoothed up algebra will coincide with the KK invariance of the bigger, the Kasparov invariance of the bigger C-star algebra. So it has also nice properties. I mean, simply the bootstrap class is the class that you get from, let's say, commutative algebras and by doing cross products, long exact sequences and so on. And then for each of these constructions, you can carry over the isomorphism. And I mean, it's not a very deep result, but it's just an observation. And that's on the bootstrap class, it will always work that you get the nice situation. And also, the fact that Kk is a universal functor immediately gives you the bivariant joint Kohn character, simply because HP star of AB also has these critical properties. And Kk star is universal. So universal means that you have this map. And actually, again, you can show, because the left-hand side and the right-hand side have similar properties, that on a natural bootstrap class of algebras, this will actually even be a rational isomorphism. There's one additional remark here. I mean, this joint Kohn character here is completely abstract. It's based on just abstract nonsense, namely universality of the functor. But there is a kind of a more explicit connection between Kk and cyclic homology, which is based on the structure of the algebra little qa and the algebra ja. Namely, it can be shown, I think the first time it was done in a joint paper with Alain, with me, that cyclic cocycles on an algebra can be described exactly as being traces on the powers of these two standard algebras, universal algebras, little qa or ja. So if you take powers of these and you take traces on these, you get exactly all the cyclic cocycles. Okay, now one more thing. Now we're getting more and more algebraic. I mean, the title of my talk was the algebraic approach to KK theory. Now you can apply this, what I just told you, namely the little KK theory for locally convex algebras. You can apply this to just ordinary algebras over the complex numbers. I mean, they should have a countable basis. If you take just any algebra over the complex numbers and it has a countable basis, then you can consider it as a locally convex algebra, taking the fine locally convex topology. The fine locally convex topology is defined by allowing all seminorms on this space. And an important, we can apply the algebraic version of the KK theory, namely the little KK, and see what it gives. And a motivating example for me was the Weil algebra, which is a very important algebra also. It's the universal algebra generated algebraically by two elements x and y, with satisfying the commutation relation that xy minus yx is equal to 1. Now, it's very easy to see that this algebra cannot have any traces, for instance, and also it cannot have any submultiplicative seminorms. So, but it's still a locally convex algebra. I mean, of course, you cannot embed it into any Banach algebra or locally convex algebra with submultiplicative seminorms, because this commutation relation shows that that cannot exist. But the KK theory can be computed using the definition which we just discussed, and the computation of the KK of the Weil algebra uses a suitable extension. It's a kind of triplets type extension, And one can show that the Weil algebra is, in fact, equivalent in this KK theory to the twofold extension, but by Bott periodicity, then it's actually even equivalent just to the complex numbers. And we can apply the Chern-Kohn character and get a map from the cyclic from KK of W, C to HP star of W, C, which is known to be, again, the complex numbers, but the generator of HP star of W, C is not generated by a cyclic cocycle of degree 0, not by a trace, because W does not have any traces, but is generated by two-dimensional cocycle. So if you want, geometrically, W looks like a two-dimensional plane, and it has no points, because every point would give you a trace. And so, okay, I mean, that's geometrically, I mean, it's kind of plausible. And of course, one can generalize this result for the Weil algebra to other algebras that involve such commutation relations which lead to necessarily unbounded differential operators. Okay, all this can also be described in the framework of logical algebras, and this described in a joint book with Ralph Meyer and Jonathan Rosenberg. Now, since we are here with arbitrary algebras over the complex numbers, you can look at the so-called Leavitt path algebras over the complex numbers, and we can again consider them as a locally convex algebra with a fine topology. And again, one knows, I mean, really, the properties of this little KK are so similar to the properties of capital KK for these algebras that you can kind of reproduce the computations. And so it's not difficult to compute the invariance, the little KK invariance for these Leavitt path algebras. And you find the same things known from C-star algebras using similar arguments. Namely, in particular, get the Baron-Franks invariance for the matrix and so on. But one can do even better. And this has been done by Willy Cortinaz and Andreas Thom. Namely, you don't even need an algebra over the complex numbers. You can take much more general algebras. Let's say, let's restrict here to algebras over a commutative count ring. And one can, again, develop a version of KK, of this Pythagorean K-theory, using the suitable categories, the suitable notion of extension, suitable notion of homotopy, suitable notion of stabilization. So the suitable notion of homotopy in this case will be just the algebraic homotopy, which means polynomial homotopy. Stabilization will be just tensor products by finite matrices of arbitrary size. And well, extensions are extensions, I guess, with a split. And so Cortinaz and Thom study the theory as described before. And basically using the same formula, I mean, you just take exactly the same formula, but replacing homotopy classes by algebraic polynomial homotopy classes, describing, replacing a stabilization by this algebraic stabilization, and replacing the ideal in the universal extension by the ideal in the universal extension in this case here. Okay, and so you get a category, which, I mean, all these categories which I described are triangulated categories. And again, this little k is a universal functor, which is homotopy invariant for this kind of homotopy, stable and half exact. It has, in fact, long exact sequences also. And again, they can compute the coefficients, and that's also an interesting result. Namely, they get something which has been known before, namely homotopy invariant version of Algebraic K-theory. Algebraic K-theory is not homotopy invariant, but you can make it homotopy invariant, and that has been studied by Weibel And the result that you get for the K-theory defined by little kk is the kh star, the homotopy invariant algebraic K-theory of A. And then one can also again compute the Kk invariance for the Levit path algebras over such a commutative ring. And the methods are not exactly the same as in the C-star algebra case, but still somewhat analogous. And so it's very computable. And in fact, I think also Cortinius used it to even classify Levit path algebras up to homotopy by the Kk invariance. Also a result that had been known for C-star algebras. Okay, so I guess I've already taken a little overtime, so I think I stop here.
All right, thank you so very much, Joachim, for such a nice talk. We have about 127 participants, so hopefully we get this right. So if you have questions or comments, please go ahead and ask one by one. We are going to manage. Please.
Well, maybe I can just ask a question to Joachim in the following way. I mean, you know, first of all, there is this sort of a margin between the smooth and homotopy invariant, which can be tested in a very significant case, which is the Novikov conjecture. So what I mean is that we have from a group cocycle, we have a cyclic cocycle on the algebra of the group ring. So it can be probably, I mean, in some cases like hyperbolic groups, it can be extended to the Schwarz algebra, which is stable under holomorphic calculus, and then you get a Novikov conjecture because the K-theory is the same as for the homotopy invariant world, which is the C-star algebra. Mm. So my question is, I mean, it seems that the tools that you have, you know, could exactly handle this type of problem. I mean, in the sense that, for instance, you know, there is the work of Vincent Laforgue on KK-ban,
yes,
and so on, where, okay, one can see that variations on the homotopy invariant case can be extremely powerful. So my question is exactly where does one stand with respect to the direct attack on Novikov, which would be to take the cyclic cocycle, and then try to have a theory which has both properties, namely it pairs with the cocycle and it is homotopy invariant.
I did not quite get the question at the end.
Well, my question is the following. You see, there is a kind of sketch of a proof of Novikov, which yes. is that you take a discrete group, you take the group ring, you know that there is a cyclic cocycle associated to the group cocycle, and yes. And then what you want to pair it with the signature.
Mm-hmm.
But the problem is that okay, you can even define the signature as an element of K-theory of the group ring, but you don't know that it is homotopy invariant.
Mm-hmm.
In order to use the homotopy invariance, you have to pass to another category, which is C-star algebras mostly, or perhaps Banach algebras and so on. So what I mean is that there is this frontier, if you want, between the two. And I wonder whether, with the freedom that you have of choosing the category and so on, one could sort of go through this frontier. I mean, but what I am saying is that the case of the Novikov conjecture is really an absolute test case.
Mm. Yeah. Okay.
And,
I mean,
okay. If you want a simpler question,
I mean, the only thing
in KK-ban.
The KK-ban. Well, KK-ban is. I mean, this has nothing to do with your question, but KK-ban is not bivariant. In fact, we spent quite some time trying to look for a bivariant version. I see. Vincent Laforgue, the main difference to what I presented here is that he has a very, very general notion of Morita equivalence, which is, so he allows arbitrary pairs of Banach modules. And so here I use just a single algebra each time, but he needs many And we tried together with Paravicini for some time to find a good bivariant version, but this did not work out because of this Morita invariance, which it's very hard to incorporate. And the other thing concerning the homotopy invariance, maybe the only thing I could say in this respect is that one thing we found together with Andreas Thom is that if you want to make K-theory homotopy invariant, it suffices to stabilize by things like Hilbert-Schmidt operators. I mean, that's maybe it's not exactly your question, but I mean, in that way you can enforce homotopy invariance at least on the K-theory, algebraic K-theory, if just by tensoring with the Hilbert-Schmidt operators or such Schatten-class, another Schatten-class.
Yes. Okay, but that's very good because so what I mean is that there seems to be a direct goal, which would be to give a proof of Novikov in general, just following this pattern. And so I presume the fact that you can use Hilbert-Schmidt but not trace class is significant. No?
Well, trace class also works, but it's indirect. I mean, Hilbert-Schmidt works on the nose, but for trace class, you have to take first do Hilbert-Schmidt and take the square, and then you use the fact that cyclic homology is invariant under taking squares and so on.
Yeah, sure. I see. Yeah. Okay.
Yeah, you could also L-vol. You could also take trace class. Yeah.
Well, okay, but then if you could take trace class and you have the homotopy invariance, then if you have trace class, you can just extend the cocycle by tensoring with a trace.
Yeah.
So then, okay, I mean, it looks like a reasonable thing to try.
Yeah, maybe.
Yeah.
I
Will
point out, in this respect of what Alain was saying, there is this result by Woliang Yu that the rational assembly map is always injective if you tensor with the union of all Schatten ideals. And this is a result of Woliang, and I have a proof of this with Tartaglia that goes along these lines that you map to cyclic homology and show injectivity and use trace class and blah blah blah.
Sure. Okay. So, but I mean, I think this is at the heart of this discussion. Namely, to know whether with this type of ideas one could prove the Novikov. I mean, really. I mean, I think it's really the good question somehow. I mean, I'm trying to do it.
Maybe I can ask a question.
Yes.
And in your paper with Alain, you have introduced a concept of positive traces and then positive, which correspond to the positive co-cycles on the algebra.
The concept of what?
Positive traces and
positive,
the positive co-cycles. Yeah. And I wonder if in the later development related to what you talk about, what you discussed today, is there anything?
Alain is still thinking about it, but I have not thought about it for many long time.
Okay.
But Alain, you are still interested in that question, I guess.
Yeah, well, I think it is interesting, but for totally different reasons. I mean, it's interesting because of the link between positive Hochschild or cocycles and the conformal geometry. But I mean, this is a different story. I mean, it's really the relation between effective representatives, not up to homotopy, and geometry. So I mean, it's a different aspect, quite different. From what you explained.
All right. Are there other questions? Comments?
Okay.
All right. In that case, thank you very much again, Joachim, and thank you everyone for coming. I'm going to stop the recording, but I'm going to leave this session open in case you want to discuss informally or you want to have a beer or something. So I'm not going to close the meeting. Up to you. Thank you very much. See you next time. Thank you.
Thank you.
Thank you.